This problem string was designed by Pam Harris of mathisfigureoutable.com. It aims to develop an awareness of and skills with the over strategy in division. It was an incredible buzz to co-teach this problem string lesson. Class itself had been working on problem strings for a little while now, but this was a lesson where it really came together and it felt and it seemed really successful for a number of reasons. There was growth in several areas. Engagement, their capacity to reason and their willingness to reason, incredible growth in confidence, and really importantly, growth in persistence. When they got stuck, and it was really early on, they were prepared to keep going and having a go and trying to work things out. So what contributed to or supported growth across so many areas? The setup and expectations are a crucial part of a problem string. Let's start with seating. So students are sitting on the floor, they have their whiteboards and they have their marker and eraser. When students have an answer, they put their thumb against their chest. On some occasions, there may not be just one answer or one strategy or one approach, so we encourage students to come up with multiple approaches, and then they can signal that by putting two fingers against their chest if they have two different ways of solving the problem. Then we ask students to chin it. So they place their whiteboard underneath their chin, and this is an opportunity for the teacher to check students' answers and to also mentally note students who are having difficulty so that they can provide prompts or support to those students. In respect to expectations, we have a go attitude. We encourage students to persist. And we expect to learn from mistakes. We recognise that mistakes are okay as long as we unpack them and learn from them. It's really important for students to recognise that maths is an iterative process, meaning that we don't just do it in one go all the time, that it's okay to have version 1, version 2, and we're constantly reflecting and redrafting and rethinking and improving what we're doing and learning from what we're doing and the mistakes that we're making. So let's get started. The first problem in a problem string is a helper problem. The helper problem is designed to assist us with the next problem in the string. So the student said, well, 600 divided by 6 equals 100. Okay, next problem. 594 divided into groups of 6 equals, or how many groups of 6 equals 594, given that we know 100 groups of 6 equals 600. So this notion of groups of 6 is a really important aspect here. This question really stumped students for quite a while, and even when they came up with their answer and signalled it by putting their thumb against their chest, they didn't seem that confident. We asked them to sort of rate their confidence, and for a lot of the students, they weren't really confident. Some of them had answers they thought might be close, but some of them thought, no, I'm way off. Here's where questions and prompts are critical. How can we use the helper problem to assist us? What do we already know about the problem that can help us? So here's our helper problem. How can we use that to help us with this next problem? That helper problem tells us that 100 groups of 6 equals 600. But we want to know how many groups of 6 is 594. So off they went, trying to work it out. So we asked the student to chin it, to show their answers, hold up their whiteboards, and there are a few students who had the correct answer, but the most common error that students came up with, or most common answer, was 94. They were thinking that 94 groups of 6 equals 594, which was incorrect. When we dug into the 94, students were saying things like 600 minus 594 equals 6. So then we do 100 minus 6, which is 94. Here we need to redirect the students back to what do we already know and what's the question asking us. Also, what do we notice about the numbers in question? So we already know that 100 groups of 6 equals 600. And then we want to know how many groups of 6 equals 594. So let's look at these two numbers. What do you notice about those numbers? How close, how far apart are they? How might that affect your answer here in terms of groups of 6? Off you go. Recheck or confirm your answer, rethink it or change it based on what you know about this problem and this problem string and the strategy we're using. Let's unpack. What's the difference between 600 and 594? So it's 6 difference. So they're really close to each other, and that 6 is one group of 6. One group of 6 makes 6. But if we have 94 groups of 6, then that's 6 less than our 100. 6 groups of 6. 6 groups of 6, which is 36. So that's too much. That's taking away too many groups. So our answer is going to be too low, especially when you look back at our numbers, 600 and 594, and there was only 6 different. So that was one group of 6. But here now we're talking about 6 groups of 6. So here's a useful way to represent our thinking here. 100 groups of 6 equals 600. What's the difference between these two numbers, 600 and 594? Difference is 6. And we're working in groups of 6, so that's one group of 6. So if we know 100 groups of 6 equals 600, and we take away one group of 6, we have 99 groups of 6 to give us our total of 594. So 99 groups of 6. Here's the next helper problem. So student said 100. Okay, how can we use this helper problem to assist with the next one? It's really important to have representations of students' thinking prominently displayed, so students can use this representation to help them in terms of how they might represent their thinking. There was a noticeable increase in confidence in approaching this problem. So then we asked them to chin it to show their answers, and interestingly enough, most of the students came up with the correct answer, 99. So they said 100 groups of 4 equals 400. In this example, or this problem, we've got a total of 396. So what's the difference between these two? So there's 4 difference between 396 and 400. So that's one group of 4. So if we take away one group of 4, equals 4. 100 minus 1 is 99. 100 groups of 4 minus one group of 4 is 99 groups of 4, which gives us 396. The next problem was 1,200 divided by 12. No problem, said the students, that's 100. Okay then, use this helper problem to assist with the next one. 1,188 divided by 12. Confidence again was high, and so they said, well, 100 groups of 12, that gives us 1,200. But in this problem, we've got 1,188, and we know that there's 12 difference between those. That if we add 12 to 1,188, we'll get 1,200. So 12 is one group of 12 there that we're dealing with. So if we take away one group of 12 and 100 groups of 12 minus one group of 12 is 99 groups of 12, gives us 1,188. Then we posed the last question, 882 divided by 9 equals, and we asked them to come up with the helper problem. Here you can support students if necessary by asking them to look at all the helper problems and noticing what they have in common. So students came up with 900 divided by 9, which they said is 100, as their helper problem. Now this problem is slightly different to the other ones in that the answer is not 99. So they said 100 groups, we know 100 groups of 9 equals 900. The number that we're looking at here in this problem is 882. So what's the difference between these two numbers? That's 18. Now we're looking at groups of 9 here. So 18 is two groups of 9. I'm going to take away two groups of 9, that's our 18. And if we take away 2 from the 100, that gives us 98 groups of 9, which equals 882. This was such a fantastic lesson in terms of the growth in all these areas. Here's what I think contributed to that success. It was a well-paced, well-structured lesson. There was a clear understanding that we were focusing on groups of. Also, that the name of the strategy that we were focusing on was the over strategy. We had a small group of questions and prompts that we used over and over, so that gave a consistency and a predictability for the students. What's also crucial is representing student thinking in a clear way. Now, you won't always get this right straight away or first time, and sometimes it only becomes clear as you work through problems with the students. But I think it's really beneficial if you can work through the problem strings yourself before you give them to students and think about how you're going to represent their different ways of thinking or their different approaches or strategies to the problems. Ultimately, we want to demonstrate and model representations that they can replicate. For more thinking routines, check out my YouTube channel, Thinking Maths with Greg Curran.